and radiological protection. I also got my license in nuclear engineering, so I can legally practice nuclear engineering in a number of states where I hold my license, which means that by law, the public can rely on my calculations for safety, literally. And I've also been named as a fellow in both the American Physical Society, the Society for Physicists, and for the Health Physics Society. And I currently also hold a joint faculty appointment with Savannah River National Laboratory. I used to have one with Oak Ridge before I switched over. And I also serve on the National Nuclear Security Administration's Advisory Council for Nuclear Security. The research I do at NC State is in things like nuclear forensics, nuclear nonproliferation, radiation shielding, all the cool stuff. Just the really cool stuff. Just ask me, I'll tell you. We also do radiological error monitoring and radiation detection. Those are the kinds of things that these students over here, and public communication like this. This is what these students, these graduate students that are among us, and 2 undergraduates actually. We have 2 undergraduates in nuclear engineering here that are doing summer work with this program right now. So with that, that's who I am. And this is some nice cute little photos from my lab. I have the coolest lab on campus. Again, just ask me. I do the coolest research. My students actually might even agree with you, probably, that we get to do the coolest research. So you've heard some claims today, and what I'm going to do now is I'm going to go over the science. I'm going to do the hardcore science at this point. So there's going to be a little bit of physics lectures, but it's really on the light. It's really designed for public consumption as opposed to graduate students. In fact, what we're going to go over right now is basically the introductory lecture to my undergraduate health physics class. Most of the content here is just that. It's just the intro, the first day in class. What is it that I say to these students who really have had no exposure before? And so that's largely what we're going to, and so it's just an introduction to the science that goes behind radiation safety and radiological protection. So this is the way that we're going to do it. We're going to focus on nuclear fuel, use nuclear fuel, and then the big one. This is the one that tends to be the favorite, radiological risk in context. Then we're going to go over the impacts and requirements of, for different energy sources. And then some of the popular items that we're going to talk about, the science of nuclear accidents, terrorism, and then we're going to finish off with the interim spent fuel storage facility installations. So that's where we're going, so let's go there. All right, so the first thing to understand when it comes to why these claims can be true is energy density. Now, let me contextualize energy density. Whenever I do any other discipline, any other engineering or science discipline, it's almost invariably talking about rearranging valence electrons. So chemistry, engineering, all of these are these valence electrons that are that I'm either combining them or breaking them to do some form of chemistry or other form of design. Now, those outer valence electrons on a material, the energy difference in those energy levels that you have are going to be on the order of about 1 electron volt. So when I do combustion of fossil fuels, I'm only getting about 1 electron volt of energy per atom that's involved in that combustion process. As I'm breaking apart the atoms in, say, gasoline or natural gas or coal, as I'm breaking them apart and I'm making water and carbon dioxide, it's about 1 electron volt per atom is how much energy you get when I'm doing fossil fuels. When I do nuclear, if I'm fissioning uranium-235, I get 200 million electron volts per uranium-235 that was fissioned. 200 million times more energy per atom. Fusion, it's a similar number. It's actually not quite as big as that per atom. If you look at how much energy you can get from fusion, it's more like tens of millions of electron volts or less. But still, as opposed to 1 electron volt, millions, tens of millions, hundreds of millions. And so that might sound like magic, and that's why these claims have a solid technical basis. It's because of energy density. How much energy do I get out per amount of material that's required to extract that energy? And so 200 million, at 200 million, that's a 2 with times 10 to the 8. 8 zeros. It's just a fantastic number. And so that'll come back a lot. That'll come back a lot. The energy density that enables all of these fantastic claims is because you have fantastic energy density. Now, some other things that I'm going to throw out there right now, because these are going to come back, answer a lot of questions as we go through the science, is going to be the fission product. So when I do fission, here's an example. I could get barium-139. Barium-139, the barium, it's got 56 protons. That describes the chemistry. That determines how many electrons are around it, which is the chemistry. But it's got 139 neutrons. That's neutrons and protons added together. Similarly, krypton, it's got 36 protons in it, but it's got 95 neutrons plus protons. Those are just two different isotopes. I can get a distribution of these isotopes. So these are the mass numbers, number of neutrons plus protons, and they're going to center around 140 and 90. And so when I fission something, here's some examples up here, some examples of fissioning the uranium-235 and the different fission products that come out. And you can see these mass numbers do center right around 90 and 140. And then we'll get off some neutrons that then go off and repeat the critical system that you have in a nuclear reactor when you're doing that. But the key is I get a distribution of them, a large distribution that's characteristic of fission. And we're going to come back to that later. But the big takeaway is this 200 million versus 1 in energy density. Fantastic energy density. This is why you see that there's a large love for fusion. It's simply the energy density. Fusion creates radioactive waste. It's just not high level waste. And it's not as much waste. But it still creates waste. It still requires materials. It still has an environmental impact, but it's just fantastically high in energy density, which means that it makes it have an incredibly small environmental footprint. It's that energy density. So the whole fuel cycle starts generally and historically with digging a hole in the ground. There are other ways to do it, but that's historically how it's been done, like the offenses that have been done to Navajo Nation. Digging a hole in the ground, and obviously we want to know the risks when we go into it as opposed to allowing people to do it without mitigating those risks. You dig your hole in the ground, you then you do the milling and the milling process and refining process, which is basically you expose it to an acid to remove the mineral component from the silicate. The silicate, you're not interested in that, that's just sand. You want to get out the other mineral component that's not the silicate. Once you've got that, that's the uranium, the U3O8. You then go through a chemical process to create uranium hexafluoride. Uranium hexafluoride is just another chemical that has the ability to go from a solid to a gas with just a small increase in temperature above ambient, which makes it useful for the enrichment. You go through the enrichment. The enrichment is where you take the fissile component of uranium, which is uranium-235, which is only normally around 0.7% natural. And you have to enrich that to about 5% for commercial nuclear fuel. And having a gaseous form of the uranium hexafluoride, allows you to do that. Once you've done that enrichment, which creates also some depleted uranium as a waste product, as a byproduct, you then convert that to uranium dioxide. You sinter that and create the little pellets that go into the fuel rods that go into a nuclear reactor. Once it's in a nuclear reactor, then it goes to this interim storage, the ISFSI, the Interim Spent Fuel Storage Facility installation. Now, ideally, one would then recycle that, which we stopped doing in the past century and haven't brought back up. And so we're currently, what's on the books legally is that it's allowed, that we're only allowed to go into a geological repository. There's well over 90% of the energy still there, but we're not allowed to do that at the moment because the recycling was taken off the books a long time ago. But that's where we are right now with the fuel cycle. Well, how does a nuclear power plant work? Basically, a nuclear power plant is, for all intents and purposes, identical to any other thermal plant. Geothermal, natural gas, coal, oil. You simply boil water. When you boil water, how do you boil water? You need a heat source. Once you've done that, once I boil the water, with a nuclear power plant, we use a nuclear reactor. You boil the water. That boiled water is super hot. So you create high temperature steam that then expands in a turbine, which turns a dynamo to make electricity. Well, now I have wet steam after that. After I went through the turbine, I've got wet steam. In order to run that back through my heat source, I've got to run it through a condenser. I've got to liquefy it. And the way that I liquefy the wet steam is I pull the heat out of it. I pull the heat out of it, and it goes back to a liquid form, and I can run it back through the reactor and heat it back up again. And so for all those plants, geothermal, natural gas, nuclear, all that you're doing is providing a heat source for that water so that I can run this through the cycle. Now there are multiple ways I can do it. With a pressurized water reactor, I have 2 loops where I keep one loop, liquid water, that's pressurized, and then that converts the water to the secondary. So there's a primary loop and then there's a secondary loop. With a boiling water reactor, I boil the water in the reactor itself and then go through the turbine. So there's boiling water reactor, pressurized water reactor. The point is that you still have that same concept as with any other thermal system, is how do I get the water hot enough to boil to turn a turbine to make electricity? And that's all that we do with nuclear, is that the heat source now is a critical configuration of enriched uranium. So that's a nuclear power plant 101 concept. It's fancy rocks to make steam. As a result of this, we make used nuclear fuel. Now, even if we stopped doing nuclear energy all over the planet today, we still have to come up with a solution for used nuclear fuel. The opposition of a solution is basically a dead end. You have to come up with a solution. And are we willing to accept what science says is a good solution for used nuclear fuel? We've had problems with that in the past, is accepting what the science has said about what's the safe way to dispose of this. Because even if you don't like those solutions, we need a solution. Because this stuff exists now, and it needs to be mitigated. We need final solutions. In an interim spent fuel storage facility, we've seen some photos. Here are some photos down here on the lower left, and then here's a photo to show you in scale. So these things are about 10 meters high. They're really big. That's big enough to contain that used nuclear fuel. And these are some installations where that happens. And you can see up here on this one, the one on the left, you can see the fence there. You can't see the fence in this one, but in this one in the top right, you can actually see the fence in the background. And what we're going to learn later is that the legal dose rate at that fence is a fraction of natural background radiation. Right? Uranium comes from the ground, right? So we dig it up. And then uranium, all of its decay products are in the ground. Lisa mentioned there's 3 parts per million on average in any dirt. We'll see some slides of that later. So radiation is coming from the ground. Radon is coming from the ground. Cosmic radiation is coming from the universe around us, from the sun. And the dose rate, the legal dose rate that you can have from these spent fuel casks at that fence, or any fence, wherever the public has access to, by law, is a fraction of natural background, which means you're never even going to come close to that. Because if you do, and somebody has a detector that's calibrated a little bit differently and it shows that you violated the law, that's headlines. Even though it's just right there, a fraction of natural background. That's not something that's contextualized when you find out that a nuclear power plant violated a federal regulation. Who cares? You violated the law. That's scary. That's terrifying. And so the process is that once the fuel has gone into these fuel rods and gone into a nuclear reactor, it then goes into these casks. We'll talk more about those casks later, but this is what they look like. They're actually quite innovative. The way that the casks work is that after the fuel has cooled off in a cooling pond for 5 to 10 years, something like that, it will go in these. And these are passively cooled. So you can see these little holes down here. These are simply holes that go up to the top. The idea being that if these casks are containing fuel, the residual heat from the radioactivity will heat up the air that's in that column. The buoyancy will lift it to the top. And so these are passively cooled by convective air. The only maintenance that you need to do is to make sure that the little rodents aren't building little nests in there. And you can check that quite easily just with a thermal camera to make sure that the heat is coming off the top of it. And so the maintenance of these is almost trivial. Really, it's just security and then lockdowns, doing basic surveillances. depending on the units, you can make things look really scary. If you cast it in a light that it sounds scary. So my favorite example is dihydrogen monoxide. I don't know if any of you have heard of that. Dihydrogen monoxide, it's the primary component of cancer, primary component of all deadly bacteria. Thousands of people die from inhalation every year. It is the acid with the highest pH known to nature. Everybody that's ever ingested it has died or will die, and yet it's just water. And yet everything I said was true, right? It's primary component of cancer, primary component of bacteria. Thousands die from inhalation every year. The highest, the pH of 7 is just as much a base as it is an acid, and so the acid with that is the highest pH, because if you go to a lower pH, you're a more concentrated acid. You can cast things to sound horrible. Now let me contextualize, similarly, the used nuclear fuel problem. This comes back to energy density. That same thing I said at the very beginning, energy density. The United States has received about 20% of its electricity from nuclear for about 50 years. The biggest economy on the planet, a manufacturing powerhouse. 20% of our electricity for 50 years. That is just huge. It's an enormous amount of energy. It's almost unfathomable. 50 years, 20% of our electricity from nuclear. And all of the used nuclear fuel from all of that energy would not fill up one football field above 10 meters high. Now, if I put that number in pounds, it would be a very big number, right? These things are 10 meters high. Just the cask alone is going to give you a lot of weight. If I put that into square inches, it's going to sound big. But the truth is, energy density makes it very manageable, easily manageable because of energy density. There's just not that much, although I could put it in numbers and make it sound bad, just like dihydrogen monoxide. I can cast something to sound bad when it's not. I just spin the narrative so that it sounds that way. These casts are not indestructible, but they are virtually indestructible. If I'm going to get a license from the Nuclear Regulatory Commission to build one of these and actually put used nuclear fuel in it, I have to prove that my design will meet all of these criteria. I have to do a finite element analysis of that cask and find out what is the weakest point on that cask that if I lifted it up and I dropped it 30 feet onto an unyielding surface, what is the weakest point on that cask, and then I've got to drop it there. I do another analysis and I say, all right, if I've done that, what is the weakest point still on that cask? And I drop it 40 inches onto a steel bar. Bam! Now after this first test, it can't leak. I take that same design, that same cask, and I do this test. Bam! And it can't leak. And then I go and I bake it at almost 1500 degrees for half an hour. It still can't leak. I then take that same cask and I put it 50 feet underwater for 8 hours, and it still can't leak. And if my design can do that, I can get a license to build them and put nuclear fuel in it. So they are destructible, but they're virtually indestructible. The design specification in nuclear is, for all intents and purposes, to simplify it, the worst thing that can possibly happen is that nobody gets hurt. Imagine that. Imagine if we did that with a car. We could design a car to do that. As an engineer, I could say, yes, we could just do that. It would not be cheap, it would not be fast, and it would be very difficult to do as a one-off if we haven't done one in many decades. That'd be hard, but we could. So the design specification here is, what is the absolute worst thing that could possibly happen to one of these transportation casks if we actually put it on the road? Well, it could fall off a cliff, but it can't leak. After it fell off the cliff, it could fall onto a really sharp rock, bam, and it can't leak. This has to be on the weakest spot. Well, it could have been that it was in a tunnel fire. Whatever accident happened, maybe there was a gasoline shipment in that tunnel, and it exploded, and you've got this fire that's going, but it still can't leak. Well, maybe as an effort to put this out, we submerge it into a lake, and it still can't leak. So I can say this, as an expert in radiation safety and radiation protection, if somebody decided that they were going to try and do a terrorist activity and target one of these, my personal professional opinion is I would rather that they use ordnance on one of these than on an inhabited space. So if there was a war, I would love to see them using this as target practice instead of downtown, or even your house. Because if these go rolling down the road, I am far less concerned about these rolling down the road than you or your kids. Because these are virtually indestructible. They're not indestructible, but they are incredibly robust. And it'd be much better, in my opinion, to use these for target practice than any place where you're going to find people. My opinion. So I mentioned at the beginning that I used to work at the Waste Isolation Pilot Plant. Did all of their radiation analysis, shielding, ALARA, air monitoring, consequence assessment, basically all things nuclear. And this is evidence that it can be done here in the United States. In 1999, the Environmental Protection Agency issued their radioactive materials license. Shortly thereafter, the state issued their hazardous waste materials license, and they've been operating ever since. It's located in the southeast corner of New Mexico. Here's a cross section. The stratigraphy of this thing is quite immense. It's entirely immense. There's the surface features there, and there's the underground. The waste goes in these panels, and then up in the northern area was research. All kinds of fun research was going on there. Dark matter telescopes, double beta decay, research on particle physics, simply because it's an incredibly low background down there. Even with all this waste down there, the amount of shielding that you have here is far better than you can cost effectively obtain almost anywhere else because of the distance. I love this photo. This is a licensed certified miner with a belly box operating a miner in a mine. So I just thought that was kind of fun to see. This is a remote controlled miner, and the salt, it's easy to mine. It's soft. It's regular sodium chloride. Same stuff as table salt, except for it's got different natural inclusions of clay and other things that are in there. So it's not pure, but because it's environmental salt that you would get. And what I have here is the stratigraphy. Now, why this is substantial is because from this layer up here down to this layer down here are water evaporites from an ancient lake formation. It's a mile thick of water evaporites. Now, most of it's sodium chloride, this stuff up here, but then there's also calcium sulfate, calcium carbonate, water evaporites, basically an ancient lake that just dried up over and over again and got all of these layers that were there. And so you can see it's in the middle of a layer that's about a mile thick. The cross-sectional area for this formation is bigger than most western states. Not as big as Texas, but it's huge. That might be hard to conceive of on the East Coast, where we only have these small little states. But out west, a state is big. And this salt formation is phenomenal. And so this is what geologists would define to be what we call stable geology. The size of a salt crystal goes from what you get for table salt to maybe the tip of your thumb. And so what ends up happening is that this stuff has a property that's called elastoplastic. Under massive lithostatic pressure at these depths, the salt will heal itself. It will move. Those grains, they'll slide, the crystals will slide along those grain boundaries under those massive pressures because it's very deep. Well, in 2014, this happened. Los Alamos National Laboratory sent a drum to the WIPP that, for all intents and purposes, exploded, aerosolizing 7 curies of americium-241, a transuranic radionuclide. Now, this is what happened at the surface. What we see here on the left is basically what the waste looks like in the repository. We see these large 10-drum overpacks and 55-gallon drums up there, and you see the operators putting the waste in there. It's actually really impressive to see. The actual person controlling this fork truck is this spotter right here, and they're just giving hand signals. So that the real estate here, it's worth about $10,000 per square foot. So you want to take advantage of every inch. that you can. So they get those drums just right up and kiss each other and put it down gently. So that this guy right here, the spotter, is for all intents and purposes remote controlling the fork truck. The fork truck operator isn't even looking at anything other than the hands of the spotter. And it's just very elegant how they've been able to be so precise because it's so expensive. That real estate is incredibly expensive. All the money that you spend for that repository. But in 2014, this happened. One of the things that, and this, because I was there, I was the one that did the consequence assessment. One of the things that was innately true at our facility, as well as basically any nuclear facility, is that the main products are safety, quality, and regulatory compliance. And if you do that, if you have that completely done, then you get to put cans in the hole with excellence. Because putting cans in the hole with excellence, you might sound easy until you realize all of the regulations and standards and orders that have to be met in order to do this. Well, then how did this happen right over here? That was a comedy of errors in and of itself. But you see that green glob, that terrified people. That caused people 50 miles away, which is not even on the scale of this. If we come back here, this was basically all within that, but people 50 miles away wanted to evacuate. Oh, how would they know, right? What is the risk there? What is the risk? That's really what is not known. It's a big green blob. That's pretty scary, right? Looks like The Simpsons. Oh my goodness. That's terrifying. Turns out that if you had stood right there, worst case, right there, the entire 8 hours that the plume was going in that direction, you would have got about 3 times the natural background radiation dose that you get in one day on average as a citizen. That doesn't sound so scary anymore, even though it's a big green blob. But how are people to know that? How would anybody know that, right? That's something that like a health physicist would know, but that's something that like went to college for that and studied that, right? People in society haven't done that. How would you know? You wouldn't. You wouldn't. What you would know is what the newspaper told you. And all that the reporter knows is the best that they could do. That's it. The best that they could do based on their intent to give you news that they think you want to know about. One of the questions that often comes up is, well, the geologists say it's stable, but how do you know it's going to be safe in 10,000 years, let alone 100,000 or 1,000,000? How do you know what's going to happen? What, you're just kicking the can down to future generations if you stick this stuff in the ground, poisoning the earth, poisoning whoever's going to come next. Well, there's a place in Oklo Gabon, right there. If you look at Africa, Oklo Gabon, right there, right in the middle of that country that's on the coast of Africa, there was a uranium mine. And that uranium mine found some very erroneous results. They couldn't understand it. I mentioned before that the fissile component of natural uranium, that uranium-235, it's only about 0.7% in abundance. And it was even less than that here. Never been seen anywhere else on Earth. And they started wondering, why? How could that happen? Now, the more popular publication came from Scientific American in '76, but I also did some research on that right here. And if you look at the title of this sounds really weird. This is published Science. Ubiquity of nuclear fission reactors throughout time and space. That just sounds crazy. How is that even possible? That just sounds ridiculous. Turns out that uranium-235, that fissile component, it's got a half-life that's only 700 million years. Only 700 million years? That sounds like a really long time. Well, the non-fissile component, the uranium-238, the dominant isotope that's present in uranium, it's got a half-life of about 4.5 billion years, the age of the Earth. So since the Earth was formed, only half of that uranium is decayed away. But what you may or may not know is that radioactivity exponentially decays. That means it has this very strange temporal profile, and how much is going to be there as a function of time. Exponentially decays means that it decays really fast, in a sense. But that's if you go forward in time. If you go backwards in time, it exponentially increases. So that 0.7% today, if I went back 2 billion years ago, it's going to basically be 5% enriched naturally, which is what we have, as I mentioned earlier, for commercial nuclear fuel. That natural uranium would have had the same enrichment that we have to go through this uranium hexafluoride process today to get 5%. It was already 5%. And so when water trickled down in there, it caused it to go critical. There were multiple of these that occurred, creating quite a bit of heat, boiling out the water, and making a whole bunch of used nuclear fuel. And even though the water table had access to it, it stayed. How do we know that? That sounds like a ridiculous claim. How in the world do you get that published in the scientific literature? Well, when you look at the isotopic distribution of the metals, remember you get these different isotopic distributions of fission. When you look at those, here's an example right here from neodymium. Now neodymium has got 60 protons. But I can have different numbers of neutrons in there when we see so that the total mass number can go from 142 up to 150. That's where I add up all the protons and neutrons in there. And so there are multiple stable isotopes of neodymium, all of which having 60 protons, but having different numbers of neutrons. And this is what you see all over the Earth whenever I see neodymium, is this distribution of isotopes. So if I do a weighted average of these, I get this average mass number for neodymium, the chemical weight, 144.242. And that's just an average of these isotopes for neodymium. But with all of the other isotopes, that's not what we saw at Oklo. What we saw at Oklo was something crazily different. There, look at these. If you compare these two on the left, they're completely different. They are completely different of all these stable isotopes. What we figured out was what happened was this natural nuclear reactor took place. And so all the fission products, so if you do uranium-235, this is the distribution of neodymium that you get when it all decays back down into stables. And if I go and I take the natural isotopic distribution and I subtract that from what I measured at Oklo, I get this. And what we have is a statistically indistinguishable distribution of isotopes. This was a fingerprint of historical, ancient, geological fission in the Earth. Mother Nature made her own natural nuclear reactor, put the used nuclear fuel in the ground so that we could go back and prove it today. Geology works. Modern geology works. This is considered the quintessential evidence for this thing called the fine structure constant. This value of alpha shows that the laws of physics are the same today. Strong and weak nuclear force and electromagnetic force have not changed in 2 billion years. That is the quintessential proof of that, because of all of the physics that are required for fission require that alpha, that fine structure constant, to be a constant of the universe, which for at least 2 billion years it has. And this is the quintessential proof that that's the case, that the laws of physics have not changed in 2 billion years. And with it comes the proof that we know that we don't have to reinvent the wheel. Modern geology works. You can literally put the used nuclear fuel in the ground until it just decays into a different kind of dirt. Literally. Just a different kind of dirt. If you get good geology. Well, I had mentioned that in order to have, there's a little 3D model up here, you can look at these. In order to have any kind of a nuclear installation, including interim spent fuel storage facility installations, at the fence, the radiation has to be a fraction of what you get from natural background. Where do these things come from? Well, it's not just natural background, but there's also a lot of medical out there. If you're gray-haired like me, you might have had a stress test. I have. If you have had any kind of a broken fracture, you get an x-ray or maybe even a CT scan. Well, let's look at the risk for that. That's going to be interesting. If we do a pie chart for these, you can see that on average, this is just for US citizens, this is from the EPA, on average, the dose you get from medical per year as an average citizen is about what you get for natural. The majority of natural radiation comes from not wearing a respirator, from radon and thoron progeny, the radiation decay products of radon in the air that we breathe. You can get rid of that if you wanted to wear a respirator, but I've done that. That's not nice. Plus, I can't do it with facial hair. I'd have to shave. So I'm happy that I don't wear a respirator. But that's the majority of the dose. You can see about 5% comes from space. 5% is from internal. That's largely from potassium. Potassium is naturally radioactive. You die without it. That's interesting. Got a higher energy beta and a higher energy gamma than cesium-137, which is the dominant external dose rate source for used nuclear fuel that we put in these. And that's just physics. That's literally nothing more than just physics. When it comes to medical exposures, the biggest chunk is CT scans. That's going to be the biggest one. Computed tomography is the biggest one. But then you also get nuclear medicine, right? Those things are like magic. There are things that you can do with nuclear medicine today that years ago would have required surgery, exploratory surgery, that now we can literally do outpatient, where you walk out of the facility with all of the information being given to your provider with nothing more than a Band-Aid on the inside of your elbow. It's like magic. You know, rather than 2 weeks in a hospital bed, nuclear medicine can do fantastic things. Same with interventional fluoroscopy. Things that literally would have required cutting you. Now you get to walk away with just a Band-Aid. That is just crazy. That's crazy. All right. Radiation risk in context. So now I'm going to ask you to be realistic. If I told you that 3 days ago something happened on that day that you got 10 to the minus 5 joules per kilogram of radiation dose, how many of you would be afraid? Who knows what that is, right? 10 to the minus 5 joules per kilogram. That's gobbledygook. That is gobbledygook. That is just throwing out units for the sake of throwing out units because I know that you didn't know. I'm confident, I mean, unless you're another health physicist, you're not going to know what 10 to the minus 5 joules per kilogram is. All right, well, let's just say I told you. If it's gamma, that's a millirem. How many people know what a millirem is? Well, we've got some people who know what a millirem is. But again, what's a reporter going to know? What's a news anchor going to know? A millirem. Is that deadly? How scared should I be? I don't know. That sounds really bad. All right, so let's contextualize it. So I'm going to pick a millirem, not just because it's approximately what you get in 1 day, just because you're living and breathing. Because you're not isotopically removing potassium from your food, and you're not deep underground, shielded from cosmic rays. You're not walking around with a respirator so that you don't breathe any radon progeny and get rid of all that dose. The fact that you want to live a normal life, as you do, this is what you got. This is what it costs you. About a millirem a day. A little less. But that's on average, based on population in the United States. So if you live in the Colorado Plateau, it's going to be a lot higher. But there's just not a lot of people out there, out west. If you live in the Midwest or the coasts, you're going to get lower radiation doses. So this is population weighted. So that's our base point. That allows us to contextualize a radiation dose. A millirem, it's about a day. Just because you don't want to have all these restrictions. And you can, if you choose to do so. I think the rest of us are just going to live our lives. And that's the price, about a millirem. 5 millirem. A few dental x-rays. It's about the radiation dose that you get for a round trip coast-to-coast flight. So if you go from here in DC to LA and back, it's about 5 millirem. Is that scary? It's 5 times what you get in a day. That's what the price you pay, because you don't pay extra to have a big shield over you in an airplane. You want a nice unshielded aluminum hull because that's cheap. Or I guess you could walk around with a big aluminum or a lead umbrella. But the airlines aren't going to do that. That's just too expensive. So that's about the price you pay. Now, most people would say that's not scary. Radiation dose you get for an airline flight is not a big deal. Right? It's basically a panoramic X-ray at the dental, at your dentist's office. However, That's also the EPA limit for the amount of radioactivity you can have in drinking water that you drink from for the entire year. So I mentioned uranium comes from the ground, about 3 parts per million. Thorium is about 9 parts per million. Potassium, it's everywhere. So your radioactivity is going to be in your water. It has been your entire life. But there's a limit to what we consider safe. This is not it. This is the limit to what's legal. And we'll get to the rest of that later. But the point is that the amount of radioactivity from any source that you can legally have in your water, if you drink that the entire year, cannot give you more than 5 milligrams by law. So that's pretty profound if you think about how people would react and have reacted when they found out that the radioactivity in some water violated EPA regulations. That's terrifying. Your water violated EPA regulations for radioactivity in the water. All it's got to do is do 5.1 milligram per year equivalent radioactivity if you drank that as your primary source of water. So I had mentioned earlier that the design specification in nuclear is the worst thing that can possibly happen is that nobody gets hurt. And this is an example of that. The way that we do it in terms of regulations, radiological regulations, is how low can we go and do that with quality? Big difference between that and safety. How low can I go with radioactivity and still maintain it with quality? And do it with rigor and with excellence. We can do that on a regular basis. 5 milligram per year. So maybe that's scary. What we're going to do is we're going to go on a logarithmic scale, basically multiplying this not by 5, but 5, 2, 5, 2. We're going to go on a logarithmic scale. So we multiplied by 5, now we're going to multiply by 2. 10 milligram. 10 milligram, it's not just 10 days worth of radiation. 10 milligram is the EPA limit for off-site effluent from a nuclear facility to the nearest resident. So wherever the nearest resident is to your nearest facility, the maximum amount of radioactivity that can be released cannot give more than 10 milligram per year by law, by federal regulation. Now that would be pretty terrifying if you found out that the nuclear facility down the road released radioactivity that violated EPA regulations. In the air, that you breathe, going into your mouth, up your nose, whatever. That would be terrifying. 10 milligram is the minimum dose that you get in a year just from potassium in your food, just to stay healthy. 10 milligram. If you're a small petite female or a child, it's about what you get. Potassium is literally essential to life. Your cells will concentrate it. The extracellular fluid will concentrate sodium. You've got to have a gradient there to be healthy. And so the more cells you have, the more potassium you're going to have. So multiply this by almost 5, 40 milligram. If you're a large muscular male, you've got a lot of cells. You're going to get about 40 milligram per year just because you're a big, husky, healthy man. Because those cells require more potassium. The potassium, as I mentioned before, has a higher energy beta and a higher energy gamma than cesium-137, the dominant radionuclide and used nuclear fuel that gives you external dose. The external radiation from these is overwhelmingly cesium-137, which has a weaker gamma and a weaker beta than potassium. So that's just to be healthy. Is it scary yet? Have we been scared yet at all by these doses? Let's go up by a factor of 2, 100 milligram. If you've had an x-ray to the hip, that's about 100 milligram. Now, I can assure you, you would far much prefer having 100 milligram if you bust a hip so that a physician knows what to do. Most physicians won't even treat you unless they know what happened inside. Like, why would they risk that? It could make it worse than they did better. They got to know what's going on inside you. And all it costs is 100 milligram. And then they can safely treat you. They know what to do. They know what's happening. They can see it. 100 milligram is the limit to the fence from any nuclear facility. So wherever my nuclear facility is, whatever that fence is, wherever a cowboy can go up and pitch a tent, or a homeless community can come up and live, or anybody else can go up and get as close as possible to that used nuclear fuel storage facility or nuclear reactor, any nuclear facility at all, 100 millirem per year. Now, as a general rule, a facility is not even going to let it come close to that. Not even half, not even 50 millirem per year. Again, because the consequence for violating that regulation is headlines. Literally, headlines. I mean, imagine it. A nuclear facility, especially if it was making electricity, that's like the worst. If I'm making electricity and I violate a federal regulation for radiation dose off-site, that's going to terrify people. Visceral terror at 100 millirem per year. Let's keep going up. Oh, 320, yeah, so that's about what you get in a year. So it's not quite a factor of 5. But the point is that this is about what you get in a year as a member of the public in the United States. Population rate. This is why 1 millirem per day is about what you get, just because you choose to live a normal life. So this is about what it costs you on average as a member of the United States. All the natural sources combined give you about 320 millirem. Is that scary? You don't think it's scary? All right, let's keep going up. Logarithmic. 1,000 millirem. Now, I've had a stress test. That cost me about 1,000 millirem. It's about the dose I got. I've also had a CT scan of my head when I was born. It cost me about 1,000 millirem. If any of you had a CT scan of the chest, torso, or hip, it's about 1,000 millirem. Is that scary? You might not think it's scary, but think about this. By law, the Environmental Protection Agency can recommend evacuation if members of the public can get 1,000 millirem in 1 year. In 1 year, if you can get that from any kind of a radiation event, the EPA can recommend evacuation to the governor. How terrifying is that? If you were told you had to move from your house, I might think that there's a forest fire down the road. That's terrifying. But 1,000 millirem is enough for us legally in the United States to recommend evacuation. I mean, how bad does it have to be to be told to move from your house? That has got to be terrifying. But that's a standard dose for standard medical procedures in the United States, around the world. Because the benefit that you get from this is just phenomenal. I mean, literally, when I had my stress test taken, I walked away with a Band-Aid. And that allowed my provider to see how my valves were working, my heart was working when I was having issues. Right in that area, in my chest. No cutting, no surgery, a Band-Aid. And I walked out the same day. No pain medicine, nada. It was amazing. And it was about 1,000 millirem. Let's go up a factor 5. 5,000 millirem. What's got to really be scary, right? This is 5 times the threshold to cause evacuation. This is a legal dose to a radiation worker in the United States. It's considered safe if you assume this thing called linear no threshold. If you assume linear no threshold is true, which means if you assume that any radiation is going to increase your cancer probability, the likelihood of getting cancer from that is so low that it's considered comparable to normal, safe working environments by OSHA. So OSHA has limits on what's safe for industrial risks. 5,000 millirem is that. So it's not just making electricity. This is radiation workers at hospitals, radiation workers in universities, radiation workers for industrial radiography, for if you're doing blood irradiators, if you're doing any kind of nuclear work. 5,000 is the legal limit on what you can get. Oh, and I skipped something. Even though 1,000 millirem is the threshold to recommend evacuation, if every year after that, you can get 500 millirem per year. They can maintain that, which is basically right around natural background radiation. And they can continue to not let you back into your home if you can get in 1 year from the artificial radiation the same that you're getting on average from natural radiation. Okay, we finally hit a threshold. 10,000 millirem. There's one, maybe two journal papers that have shown that at 10,000 millirem, you actually can get a statistically significant increase in cancer probability. So now you can start to be concerned. As a health physicist, now you can start to think about it. Risk versus reward. Is that worth it? Well, the hard science is that overwhelmingly yes, because the reason why we know this is because of children that have gotten radiotherapy. So by literally curing their cancer and then watching them the decades after, we found that it does increase their cancer probability by a little bit, but it cured cancer. And then when they, for those secondary cancers that form, you treat it the same way, if it's in the same place. So modern medical science says, yes, this is totally worth it, because this is how radiotherapy works. And it's a cornerstone, along with chemotherapy, with treating cancer. To put that in context, if you live long enough, probability of you getting cancer is about 40%. You don't die from something else. And so if you're getting radiotherapy, if you're a child, 10,000 millirem is the threshold. For adults, it's more like 20,000. Children are just more sensitive. So now you can start to realize that we have measurable risk. Now we have measurable risk. Up here, we have regulatory limits. Down here, we have measurable medical risks. Let's go up again. Order of magnitude. 100,000 millirem or 100 rem. The only reason we really have data up here is from the atomic bomb survivors. And here at 100,000 millirem, it's about a 5% probability of getting cancer. So over and above the 40% from everything else, you're going to get an increase there. This is a massive dose. This is like literally being exposed to nuclear weapons. Keep going up. 500,000. At 500,000 rem, now we're talking about we're not concerned about cancer. This is not cancer. This is what we call acute radiation syndrome. You get that, we call this a lethal dose of radiation. It's called the LD5030. That means that in 30 days, 50% of the people that get that kind of dose will die without medical attention. What happens here is that the dose is so big, this is a massive dose, that it compromises your bone marrow, which is very sensitive to radiation. It makes a lot of cells. And you compromise that bone marrow, you've compromised your immune system. People that get this kind of a dose are effectively comparable to later stage age patients. You have no immune system. You need a hospital bed right away, because you're probably going to need antifungals, antivirals, antibacterials. You have no immune system. Now, if you survive that dose, a lot of people will, half of them, then you can start looking at the increased cancer risk. But right here, you're looking at acute radiation syndrome. And by the time you go all the way up to 1,000,000 millirem or 1,000 rem, then we're talking effectively hospice. Now we're talking about pain medicine, humane treatment. Now you'll survive this if it's protracted. Many people have got these over if they're protracted. But if it's acute, like from an accelerator or an atomic bomb, then we have not seen anybody survive. All right. So putting all this in context, all of these values up here are where regulatory limits are. At those regulatory limits, and we've been looking at this for over 100 years, radiation effects in humans. And all of those doses up there, we have yet to see any measurable medical effects. That's where the regulations are. Down here, we don't even approach those unless it's at something like Chernobyl. Chernobyl, you're getting doses like this, the emergency responders, where you get up to lethal doses, or atomic bombs. The key is that up here, where the regulations are, and so I adjure you to think about this. How much time, money, and fear does something that has no measurable medical effects warrant? The United States, it's billions of dollars. Billions. Yucca Mountain, it was able to show that it was having a hard time being able to prove that it would do 15 millirem per year. That terrified people. 15 millirem per year after 10,000 years. Terrified people. So we spent over $10 billion. The WIP site, remember that 3 millirem? $2 billion. I mean, you might think that was money well worth spent, but I think that there are a lot of social programs, schools, housing. I think a lot of things, better things to do with billions of dollars than avoiding doses up here. But that's what we do in this country, because that's the terror. Now, you might think that sounds silly, but how many of you knew what 10 to the minus 5 joules per kilogram was? Or even a millirem? That's gobbledygook. That is gobbledygook. But we know that in this country, that's where we are. So the amount of fear, time, and money is fantastic to avoid things that are orders of magnitude below levels that have anything measurable. Orders of magnitude below it. It terrifies people. So if you don't know, you don't know. Right? I got a PhD in nuclear engineering. I do know. But that's a pretty rare thing. That's a really rare thing to really understand. All right. So I told you I'd show you these graphs. Potassium. You can see potassium goes up to, it's concentrated on the Colorado Plateau. You can see it's also concentrated in the Mississippi Valley, where it's worn out through evolution, or through geological weathering. Thorium comes up to about 10 parts per million, and it's more uniformly distributed. Uranium, again, rather uniformly distributed, but it goes up to about 3 parts per million. So thorium is about 3 times higher than uranium. And then we have cosmic rays. And you can see again, you're going to get dominated up on the Colorado Plateau. Well, out west, it's very sparse, right? The majority of our population are on the coast and then in the Midwest. And that's where we get that, over 300 millirem per year. And so this is simply because we're not living deep underground, we're getting the radiation from these. This is natural. Okay, so now we've done radiological risk in context. Now let's look at environmental impacts. So what we're going to look at are life cycle emissions, and basically what are the impacts of these different energy sources. There were some questions earlier about it, but now we're going to look at some hard numbers. When we do that, the first thing are the emissions. Right? Why are renewables important? It's because when they're deployed, they do not emit greenhouse gases. Now, obviously, whenever we make this infrastructure, there's going to be greenhouse gas emissions if we're using fossil fuels to make the infrastructure to get the energy. Well, the United Nations put this together. This is just one example. But what you'll find is that nuclear is going to be the lowest. So I'm not saying you get a lot of greenhouse gas emissions from building the infrastructure for renewables, but it's interesting that of all the options that are out there, if your concern is greenhouse gas emissions, nuclear is the most effective. Comes back to that first slide, energy density. I can get a massive amount of energy for just a tiny amount of material. So all the mining and milling, the manufacturing, transportation. If I have high energy density, all of those are made smaller. And so that's why you'll see nuclear, at the worst and best case, is better than all other options. Even in the worst case, pick any country of these countries, even in the worst case, it's still better than the best case of anything else. If that's really your concern. Now, not everybody's concerned about greenhouse gas emissions. But we are. Critical minerals. Different technologies require different materials. for all of those different materials, how much is required for each energy source? Because I think Scott kind of made this point at the beginning, we don't want a whole bunch of mines. How do we have as few of mines as possible? How do we minimize the number of milling facilities? How do we minimize the number of manufacturing facilities? We don't require a lot of materials, and that does that. Well, the only one that's better than nuclear is hydro. I can really minimize that with the hydro when I build a dam. Well, there are impacts from the dam, but all I'm looking at here are critical minerals. How do I minimize that? Interesting, photovoltaic and wind are the worst. They still don't emit greenhouse gases when they're deployed, but they are low energy density. And that's where the penalty comes from in being low energy density, is you need a lot of materials to get the same amount of energy if you have low energy density. With large energy density, you only need a small amount of materials. Scott also mentioned this. When I'm deployed, how much land do I need to take up? Now, there are a lot of us, I'm one of them, that just love the idea that we as a society have made it a law that there are places in this country that you are not legally allowed to do anything but look at. The only infrastructure you're allowed to have there is the infrastructure that will enable you to go and look at it. That's it. You can't do anything at the national parks but look at it. That's the point. Now, for me, I don't think it's in our advantage, or I think Scott would really champion this. Just because you see open land doesn't mean you need to go and fill it. When you see open land, I mean, it makes sense to do agriculture, but just because it's open, does that mean I want to go and put infrastructure there? Some people think that's appropriate. Matter of opinion. But if you want to make the least amount of impact in terms of land use for energy, you want high energy density. That means that you use up the least amount of land to get out the energy that you need. Now, this is a logarithmic plot. So every time I go up one of these, it's just like that radiological risk. Every time I'm going up one of these increments, I'm multiplying by a number. I'm not adding a number. So it's logarithmic. So what you see is that nuclear is orders of magnitude below renewables. Now, remember, renewables, traditional renewables, they don't emit greenhouse gases during emission, but they take a lot of land. And so if you're like me, you want to use as little, the least amount of land as possible. And of all the energy options out there, it's no surprise, the most attractive from that perspective is the one with the highest energy density. It comes back to that first slide. I told you we're going to come back to that. And here's an interesting one. Again, the United Nations put this out. Why I thought this was interesting is that if you look at total carcinogenicity per terawatt hour, what's interesting is that nuclear right here is lower than photovoltaics or wind. Now, is that saying that, I'm not saying that this is because of the rare earths that you have to get, right? Like wind, you're going to need neodymium. You have to dig up a lot of dirt to get the neodymium because it's only in trace quantities. But with that neodymium comes naturally occurring radioactive material, and there are going to be emissions. Scott said that in nuclear, we're the only ones that have to control that. When I'm doing traditional renewables, they don't. And so that just gets released to the environment. So this is saying, the United Nations report here, that nuclear has the lowest when compared to us. Now, don't get me wrong. I'm not saying that wind and solar are some big cancer cause. They are as safe as you think they are. They contribute to public cancers as little as you think they are, as little as you think they do. There's nothing to be afraid of. My point is that nuclear is still lower. That's what they found. Life cycle, from cradle to grave, due to dose, this is just using linear no threshold, again, you would have a higher risk from low energy density sources. Even though one of them is specifically radiogenic in origin. It's just that low. The energy density is just that high. All right, so now now that we have some information, let's contextualize these narratives. 3 Mile Island, Fukushima, Chernobyl. 3 Mile Island. The reason why I started at 1 milligram, that daily dose, is because that was the average dose to a citizen around 3 Mile Island during the event. That still terrifies people to this day. And the entire radiological consequence to the public on average was about 1 milligram. But now you know the milligram. And now you know the consequence from 3 Mile Island, which to this day evokes visceral fear. That's another example that cost the United States billions of dollars. Billions. Milligram. But they're starting it back up because they need the stable power. And that was just one unit. There were 2 units there. All right. What about Fukushima? Right, that exploded. That wasn't just a meltdown. That was a meltdown, 3 meltdowns, 3 out of 4 reactors, full meltdown, with an explosion and a radiological release. Well, perhaps you remember that the threshold to allow evacuation is 1,000 milligram. Still, over an order of magnitude below the threshold to get measurable medical effects. And most of them got less than that. The average was something like 75% of that threshold. The only people that died, the only members of the public that died from Fukushima were those that died in a panicked evacuation. Now, a 9.0 earthquake, that's basically biblical in scale. 14-meter tsunami, that's just unbelievable. That just spins the mind. That killed about 20,000 people. That's not the narrative that you hear about Fukushima. 20,000 people dead? That's not what you hear. What you hear is a nuclear power plant. Which means that these people, the ones that died in the panicked evacuation, literally risked and lost their lives to avoid something that would not have had a measurable medical effect. Not scratch, not sneeze. Nothing you could point to and say that was caused by the radiation. And they died for that. Again, who knows what 1,000 milligram is, or 1 rem? What's a rem? I don't know. Came from that nuclear power plant. They're telling me to move. That's terrifying. That is viscerally terrifying. But how are they going to know, right? 10 to the minus 2 joules per kilogram. Right, now we're talking a rem. What is that? It's gobbledygook. But that was Fukushima. That's how bad that was. Remember, the Western design for nuclear, even back in the 70s, was the worst thing that could possibly happen is that nobody gets hurt. Well, that would have occurred if they had not panicked in the evacuation. There would have been no measurable medical effects. The United Nations, World Health Organization, all the review papers made it quite clear. All of the doses were more than order of magnitude below the threshold for any observational effects that would be radiogenic. The only effects were based on fear. And that's what you hear, not about the 20,000 people that died, but those that died in a panicked evacuation. All right, well, let's talk Chernobyl. Man, that's a scary thing. That's a terrifying thing. Chernobyl, almost a comedy of errors. Never would have been legal in the United States or in the West. It's a horrible design. We knew it at the time, we said it at the time, but it was cheap. Chernobyl, that caused dozens of deaths outright from acute radiation syndrome, going up above that 100 rem level for the liquidators, the responders. Many dozens. Now, that's incredible. If you look at the cancer rate, the literature shows there are about 4,000 excess cancers. Now, most of those are treatable, but still, right? The thyroid cancer, The people that got that, they're going to be doing iodine pills for the rest of their lives. That's not trivial. Thousands of cancers, dozens of dead outright. Now I'm going to tell you something that's going to make your jaw drop, possibly again, if I haven't been doing that enough already. There was a cohort of Estonian workers. This cohort was impressive because during the time of the former Soviet Union, there were many men from Estonia that were in the military. And they were sent off to go and clean up Chernobyl. Well, there were lots of men that were not in the military. And so after Chernobyl, those men went back. And Estonia was one of those countries, one of those areas, that was largely untouched by fallout. So basically no effect. So you could go back and you could find men had the same lifestyle, same genetic distribution of ones that did respond to Chernobyl and that didn't. Right? They ate the same food, they lived the same lives, they dated the same women, right? Some went to Chernobyl, some didn't. And you can look at the disease rates between the two. And the first study came out in 2016 and didn't find anything. If there was anything, it was too small. But in 2023, they came out and they found there was a small increase in the Chernobyl responders. No surprise, right? They had increased cancer rates. It takes a while, it takes 5 to 20 years for these things to show up. And so that wasn't the big surprise. Now let me drop your jaw. They did find a massive increase in something else, both times. It was hundreds of % increase in suicide rates. The liquidators, the ones that responded to Chernobyl, had a massive increase in their suicide rates, and they found out why. It was because they lost hope. How many of you knew what a millirem was? 10 to the minus 5 joules per kilogram. A rem. What is a soldier going to know? About the same, right? That's what a soldier is going to know. And if you knew that you'd been exposed to Chernobyl radioactivity, how would you interpret that? I can tell you the way they did. They had a much higher probability of attributing any otherwise normal health consequence that's not radiogenic to Chernobyl. How do you know, right? Do you know that Chernobyl didn't cause your arthritis? Right? Did you know that Chernobyl didn't cause your hearing to go when you got older? Right? Do you know for sure that Chernobyl didn't cause your irritable bowel syndrome? Those are not radiogenic effects. Those are normal effects, and there are a lot of those. But are you going to know that Chernobyl didn't contribute to that or cause that? So that every time they had anything that wasn't an otherwise healthy experience, you could always say, it was Chernobyl. And so every time something would happen, it becomes a self-fulfilling prophecy. You have no hope. And what kind of things would you expect from people that have no hope? They would do something desperate, possibly. And that's what happened. And so what's crazy is that even with Chernobyl, not just Fukushima, the majority of deaths are from fear. Even with Chernobyl. That's insane. That's just crazy. But again, unless you have it in context, how do you know? You don't. That's the point. So we looked at these numbers before. Fereshte looked one up online. This is the one I like to use. These are the two I like to use. When you talk about how many accidental deaths per terawatt hour are there. So this one on the left, this came from Statistica. It's also came from the UNSCEAR, that's the United Nations Scientific Council for the Effects of Atomic Radiation. This shows that nuclear is safer than wind, but more dangerous than solar. This is what happens when you fold in Chernobyl with nuclear. Now I would argue that's kind of like folding the Hindenburg into modern air statistics, right? Air travel, you could do that, I guess. But with the hydropower, how are people dying? Not a lot of people are falling off the dams. Some did with Hoover Dam. But the big one here came from the Banqiao Dam. It was a dam that went another communist country in China in the past century. Took out tens of thousands outright, and then the after effects took out approaching 200,000 people from a dam break. Russia's even been targeting dams in Ukraine, because you can do a lot of damage if you can break a dam. But the point is that then this other data, again from Unskier, if you say, well, Chernobyl, those reactors aren't even built anymore. The faults you had there don't even exist anymore, like the Hindenburg. Nuclear is orders of magnitude safer than anything else. Energy density. It all comes back to energy density. If you have higher energy density, you need a lot less materials. Less mining, less milling, less manufacturing, less transportation, less waste, all of it. Less land, less impact of all kinds, simply because of energy density. That's why fusion is attractive. High energy density. Literally, that's the only thing that's attractive about fusion, is an incredibly high energy density. Same thing you have with nuclear, but we have that today. Even before 9/11, by law, the containment of a nuclear power plant in the West had to withstand a jet impact. A large passenger jet aircraft would have to be able to go nose into the reactor and no release. That's the design specification we've always had. The worst thing that can possibly happen is that nobody gets hurt. And then after 9/11, we updated this. After Fukushima, we updated everything again. Again, that's the design criteria. Nobody gets hurt. Everybody walks home. Oh, I lost our train. Oh, there it is. Is it going to work? It's not going to work. All right. Well, this is a nice video if I had it. The DOE came up with now Scott did show you the blow up of this, but again, we've just come up with a new design that is going to be is as far as we can tell the safest design ever come up with for a rail car transport. And if you did want to have an SPC, this is what it would look like. And with that, I'll take questions.
Before we take questions, no, never mind.
Yeah, go ahead.
So I had a question about route controlled access for shipping materials on federal highways versus shipping them on railways. Is there any consideration for control? I guess you do not necessarily have people driving cars there, but those areas, do they still have police escorts, etc., on federal railways like they would on highways?
So it's going to depend on the state. So a lot of states, or some states, have the concern that they don't want a vehicle stuck in traffic. And so to prevent that from happening, they'll give you a police escort. That way everybody will move and you're not going to get stuck in traffic. But that's up to the particular state as to whether they want to do that as it goes through. And then they simply can provide the escort and they're going to ask you to pay for it. It's kind of like having a concert, right? If you want police to be at your concert, you're going to have to pay for it. Yeah?
Yeah. So given that uranium is finite in nature and some point is going to exhaust, and the liability for storage is just going to increase, what's your perspective on, say, the newer technologies that are not in the PRX process, but rather bioprocessing or electrochemical processing? Analytes is highly subject in the United States.
Ooh, that is a fun one. Uranium is a limited resource. So, let me put this in context. I showed you the graph earlier that uranium is about 3 parts per million. Uranium is more abundant than tin. Now, tin is required not just for renewables, but for all electronics. That's how we solder the joints together. So, it is a limited resource. But at 3 parts per million, right now, there's about 4.5 billion tons of uranium in the ocean. Now, as I showed you those graphs of uranium across the United States, I don't know if you noticed this, but they're concentrated right around the Mississippi basin because of erosion off of the Rockies mainly. Right, all that granite, it's got uranium inclusions, which has radium, which gives you radon. So you're going to get a lot more radon if you go up there, nice fresh mountain air. You have a lot more radon. But the uranium is just being dumped in the ocean. So if you use breeder technology, it's about 9 times the electrical energy needs of the United States just being dumped in the ocean every year. The plate's out on the bottom. We could passively remove that. 4.5 billion tons. And that's negating digging a hole ever. And so the amount that's there is phenomenal. Now, there are technologies that would allow us to passively remove that. They've not been demonstrated to scale. They're just laboratory experiments, national labs and so forth. And so, yes, it is a limited resource, but it is actually abundant. And there are those that would like to spin the narrative to say that we're going to run out. Because if you look at the resources we have now, and if you assume that the price has to stay at the same price it is now, and that we don't ever find any more resources, and we don't ever have technology to extract more resources, then what we're using right now would run out. That literally applies to anything, including tin, if you make that argument. That the only thing you can ever use is what we have now, and the price can never go up, and you can never have new technology. Again, it's like that dihydrogen monoxide argument. Does that make sense? Now, that's just looking at what's naturally there right now that's untouched. I had mentioned when I was talking about the fuel cycle that we have to make enriched uranium, which has more of the uranium-235. It needs to be up to 5%, which means that we create a waste stream that is depleted in that. We call that depleted uranium, where it's got about 0.2% or 0.3% instead of 0.7%. And so you get a lot more of that. And that's basically all pure, it's almost pure uranium-238. Now, your question is with breeder technology. With breeder technology, all of that can be made into usable fuel. And that's without recycling any of the current fuel, which when we throw it away, it's got over 90% of the energy still in there. And so if we were to use breeder technology, we could take all of that waste product and turn that into electricity. And so not only recycling would more than 10 times increase the amount of uranium fuel we have today. More than 10 times increase that. Of all that we've ever used, that 20%, if we were just recycle that, then we would get 10 times that, more than 10 times that back out. And that's ignoring depleted uranium that you could turn into fuel with a breeder reactor, which is about 100 times the amount that we already have. And that's without ever digging up a new hole. And now it all comes back to that same initial slide on energy density. How much energy is there? And it's fantastic. Remember that 2 times 10 to the 8? Yes. It does some incredible things when you have that kind of energy density. Good question. Other question?
I had 2 questions. One was just a quick one, hopefully, about the energy or the radiation that was released from the Gabalon naturally occurring site. What would that be on the scale of what we see in the
Oh, that would be like the research reactors, where over the, if you integrate it all up, less than about 100 megawatts. So I mean, it wasn't like explosive, because water would trickle in, it would slowly go critical, and then it would balance itself. It wouldn't go prompt critical because the water didn't come in that fast. And when it came in slow, it would approach critical, and as it would approach critical, as the heat built up, it would expel the water. And so you would have an equilibrium of the water that could come in and still stay liquid without being pushed back out. But even with all of that dynamics, the used nuclear fuel stayed there, literally. So before we do another question, I'm going to remind everybody that we have sent out the last survey. So I'm going to ask everybody, while we continue with questions, check your email and do that last survey.
So we accidentally sent 2. So you're looking for in the subject line that said 3rd survey. That's the one that you're completing.
Did we make mistakes?
Yeah, we hit the return button twice. But
Okay.
it's really the 3rd one.
Other
The
questions?
subject line.
Yes.
I want to know your thoughts on alternative fuel design reactors like the molten salt reactors,
Mhm.
et cetera, and how the potential for those to come online would affect public perception, the safety implications, et cetera, of those reactors versus the standard PWR, BWR, or the uranium fuel reactors.
So I have the personal opinion that all useful energy is good, if it's useful. That even includes fossil fuels. That's what took us out of basically living, like the Amish into today. But because we did so much of it, now we're paying a penalty. And so obviously it did a lot of good. But now we need to figure out how to mitigate the impact that we hadn't realized was going to happen. And so all energy is good if it's useful, right? That would be my argument. but we want to minimize our impact. Reiterating what Scott said, right? That just because you see open land doesn't mean you should go fill it. Maybe you think you should, I don't. I prefer that to stay open, and we'll consolidate our footprint into cities and so forth. That'd just be my personal perspective. Now, with that, there are, obviously, I would argue, far more attractive ones in terms of safety and health, environmental impact, and all forms of risk, all risk combined. So there are those. And as a general rule, just like with your retirement, if you diversify, the more diversity that you get, the healthier you're going to be overall. So that you're not relying on any one particular technology to keep you alive. Because once that goes, for any reason, it might be a low probability, it might be an extremely low probability. But the more diversity that you have, the more resilient you're going to be. And so all of those technologies are attractive. The same would apply to photovoltaics. If you're buying anything that you rely on for your life from any one source, that source could go for any reason. Political, geopolitical, natural, right? When that happens, what are you going to do if you're relying on that to maintain your life, your security, your well-being, your standard of living? The more diversity you have, the less impact it is if one or more aspect goes. So I prefer diversity because it provides resilience and agility and overall robust health, in my opinion. And there are a lot of energy experts that agree with it. Other questions? Yes?
So you mentioned like using breeder technology and waste recycling. So I've heard that countries like France, they do a lot of that. But here in the US, we don't do much waste recycling. Why is that?
It was a political decision in the past century where one of the presidents recognized that the process that we invented for recycling could be changed to create nuclear weapons. Just like the process that we invented for enrichment could be used to create nuclear weapons. And so that president decided to abandon that technology in hopes that, because we were leading in everything in the past century. This century we're still leading in most things. But the belief was that if we stopped doing it, everybody else would, because they just follow us. What ended up happening is that everybody else said, well, if the United States ain't going to recycle, we're going to recycle. They can do what they want. We have the technology, we're going to use it. And as a result, when it was made legal again, there were too many dollars lost in investments in recycling in the commercial industry for anybody really to have an appetite. Basically, when you have political instability, it's not attractive for investment because you don't know if you're going to be, what's going to happen to the rules if you have political instability. You can't predict it. If you can't predict it, you can't mitigate it. If you can't mitigate it, are you going to throw money at it? Probably not. And so as a result, for many decades, there was no investment in it. And where there was investment was in this once through, in mining and milling. And so that's what's cost effective now, because that's where we've done our R&D. And so it's no longer, in this country, cost effective to do that. We'd have to build a multi-billion-dollar facility, which does not exist. We could, but we haven't. Does that make sense? It would take a massive investment. And the government actually started to do that. They were building a MOX facility in Savannah River, but it was over budget, over schedule, and so they decided to change its use to making nuclear weapons. That's what happened to recycling in the United States. Other questions?
I just
Question.
want to add on to that, one of the most recent executive orders from our current president related to nuclear, they were all released like May 23rd of this year, or March, May. One of like the last sections, last line does say that we are going to recycle used fuel in the US again. It doesn't have any deadlines or directives like some of the other elements of the executive orders have, but it does say that we're going to do it. So that's one of the most recent updates.
Thank you. Yes?
I have one question based off of that. I think part of the executive orders is they're trying to get the NRC, among other environmental federal entities, to sunset regulations, and they're going to be having a big NRC meeting here soon where they're talking about doing away with zero threshold dose, upping the limits of the releases, etc. How do you feel that? What would be the public outcry to that? The impact of that to the industry?
Let me. That's a great question. The abandonment of linear no threshold. So the linear no threshold hypothesis is what we've used for regulations from the start, and that assumes any amount of radiation, no matter how small, is going to increase your probability of cancer. And so that means that the values, and we're up at the top, the 1 millirem, what you get in a day, that increases your cancer probability by an amount that's proportional to dose. I think that that's brilliant. I thought it was a good idea when I saw it. The more I think about it, the better it is. Because that, in my opinion, is why we spend billions of dollars to avoid millirem level doses. And why the public is terrified, viscerally terrified of millirem level doses. Why the regulations are down in the millirem levels, 5 millirem, 10 millirem per year is the legal limit. Now, that doesn't mean that you should just willy-nilly throw them wherever it is, but I can tell you this. The Health Physics Society, a professional society of people that actually are experts in this, radiation protection, radiological safety, they did an interesting poll in a meeting about these executive orders to find out what the society felt. And so one of the polls was how many health physicists, certified health physicists, actually believe in LNT. And it was a small percentage. And that was even with many very vocal anti-nuclear people attending, so it was a public meeting. And the reason why is fairly straightforward. If you look at the science, radiation is ubiquitous. If you go backwards in time through evolution, it increases. Does that mean that we're designed for higher levels? I don't know, but certainly evolutionary theory tells you that you're selected for the environment that you dwell in. That's kind of by definition. You will be selected for that environment, which is radioactive, filled with radiation. And so I think that one point was brilliant, because that in and of itself, eliminating that could completely reverse the tides for the cost effectiveness of nuclear. Now nuclear, if you look at the studies, it already is cost effective. Fresh Day talked about that a little bit because of the longevity, right? You have an initial investment, but it's the payback time is way beyond the amount to recuperate the money that you had initially invested. But a large part of that cost is risk. You have to get insurance that's going to mitigate something like Fukushima, where the remediation is, again, a small fraction of natural background. And if I've got to take cesium and get that at concentrations that are small compared to potassium, that's expensive. They're in the same chemical family. And so getting radioactivity to be a small fraction of the radioactivity that's already there is crazy expensive. And that's why Fukushima is costing so much. And that's why insurance is costing so much. But if you regulated something that's starting to approach other chemical industries, that cost just goes away, because we're not trying to minimize, we're not trying to eliminate millirem level doses. And the consensus was that the threshold before you start worrying about it is, again, most health physicists felt it should still be a fraction of background, like 100 millirem instead of 1 millirem. Some felt it should go up to 1 rem, which is even an order of magnitude below any measurable medical effects, even to children. And so by doing that, that one thing in and of itself could drastically reduce the cost of nuclear. Because again, now you're dealing with, you're controlling the risks in a way that's more commensurate with the actual risk instead of public perception. And because there is literally no scientific proof that LNT is true. It's just simple. It literally is just that. It's the simplest model. It's Occam's razor. But there's lots of science to argue that shouldn't be that way. Yeah?
So I know there's new epidemiological data from the past 20 or 30 years from radiologists, et cetera, where they're kind of starting to fill in that, and they know there is that no observed effect level. So that's adding credence to, let's increase the dose from 0 to something that's more scientifically solid.
All right, so I'm gonna go into this deeper this time.
Okay.
All right, so this is the observational data. This is the observational data. This is what we get from atomic bomb survivors, from Chernobyl. This is cancer rates as a function of dose. Now, there are multiple models that you can use to fit this. What we see is we see some lines and we see some curves. You see different functional forms being fitted to the data. When you look at these different functional forms being fitted to the data, this one right here, hormesis, is very popular. Hormesis shows, this is basically arguing evolution. It's saying evolution shows us that we're designed for the past. In the past, radiation levels were higher, so our design specification is for higher radiation. And this has been shown true for rats and mice. Because with rats and mice, if I give them a big radiation dose, rem, tens of rem, hundreds of rem, this is what happens, that I give them radiation protection. Now, there are a lot of people that say that's how we decide something's carcinogenic. That's how we define it in our societies. I feed a rat with a whole bunch of saccharin or plastic, and if it causes cancer, then it's carcinogenic at a certain level. And so, based on that standard, hormesis is real. And then that begs the question, are you a rat, am I a rat? Do we behave the same way? We certainly know for sure for psychotropic drugs, completely different. What's going to happen when I give them these drugs? There are a lot of other things that they're very different. Like if I'm dealing with Alzheimer's drugs, and I treat a rat versus treat a human, you get some completely different things happening, even with something like that. And so, maybe, maybe not, right? We know this is true for rats. We know this is true for single-celled organisms, that hormesis is real. But coming quickly to the point, all of these different models, linear with threshold, linear no threshold, all of these are down in this range of on the order of 0.01 Gray or 0.01 Sievert. So that data right there, so I've got some below, I've got some up. I mean, what's going on? With rats, I get this. With humans, I'm getting that. With humans, again, these doses are doses that are down here. These doses down here are where those regulations are. It's just noise. Literally, it's just noise. If there's an effect, we can't see it at all. Some of these models, they'll actually be hormetic. Some of these models are something else. And so the observational data is that whatever's happening down here in that tiny little sliver, it could be any of these. And there are lots of literature in the peer-reviewed publications that argue all of these. Very few actually argue for linear no threshold. It's just the simplest one. And health physicists overwhelmingly reject that. There's just not evidence for that. And its only purpose seems to be to terrify people. Question?
Okay, I don't want to interrupt,
Time for lunch.
but I have to. In the sense of, they're ready for us upstairs in the bistro for lunch. And we can continue the conversation because we're going to scatter ourselves amongst you all so we can continue, to have comments and questions answered. And I know the hour is going to go by, we're going to estimate about an hour for lunch. And then we're going to come back just to sum up, to be in smaller groups, and we can stay here and kind of distribute ourselves around to ask those unanswered questions and comments, and then hopefully come back together. We want to know how we did, right? In the sense of answering your questions, and then also what remains to be answered, so to speak, and suggestions on moving forward on how we conduct various workshops, listening sessions, presentations that we're giving. So, I think I'm going to ask Thursday to lead the folks upstairs to exactly where we're going to be, and I will bring up the rear.
Let's go eat.
I
Remember to
continue
finish that
the
third survey.
conversation.